All right. Well, my name is Danny Foley. I am a geographer here at the U.S. Geological Survey campus here in Flagstaff, mostly focused on remote sensing and Earth observation related to water use. So I'm stepping out of my usual research here to talk about a topic that I think is very fascinating. It's really a connection of how geology influences culture, art, history, society, really how geology is a lot much more than just the study of rocks and minerals, that it really is a global phenomenon. And this is a great example of a story from history. So with this, we're going to be talking about today about the biggest, largest volcanic eruption that has been recorded in human history. There has been larger volcanic eruptions. Some of you may have heard of the Yellowstone supervolcano, but there wasn't many people or any people around for those previous geological time frame, historic eruptions in time. So the Mount Tambora eruption of 1815 really stands out of the impact in the legacy that it has left behind here. Who here has heard of, just interested, show of hands, has heard of the Mount Tambora 1815 eruption before? Well, that is great, many hands, and we are in a place where we have a festival of science, the longest continuous running free festival of science of anywhere in the world, or known universe for that matter. And we're very grateful to be doing this here in Flagstaff, and it is to the thanks of the many generous sponsors, which are listed up here, and also thanks to the community for you who come here to be a part of this and show your interest. There's a lot of competing factors out there. You could be at home on the couch with Netflix, but you came out to see a talk and to support these festivals or support these talks and activities. Whether we get the star party tonight or not, I'm grateful we're all here that we can talk about volcanoes tonight. As following my talk, another USGS scientist, Morgan, will be giving a talk about the volcanoes of Arizona, which should be really cool, which you'll want to stick around for that one as well. And here we have a link to the survey. I will put this up again at the end. As Greg mentioned, the survey is important to the festival to let them know what went well, what could be improved upon next year. And this really is just done by a network of volunteers. Brandon Laurie here today, who really helps make the festival happen, and Greg and many volunteers here to keep this event going strong. A little background of who I am. I have my degrees in geology with a bachelor's and master's from ASU, where I put my photo up there where I got to do some research in Antarctica. That was cool, both thermally and metaphorically speaking. And then I went to NAU, so I am an alumni of graduate school at the Harvard of the Colorado Plateau and Greater Four Corners region, Northern Arizona University, where I studied geography, which led to my position here, which really is a dream job to be able to do science at the U.S. Geological Survey here. As you're in this Shoemaker building, this building has a long history of sending astronauts to the moon, and a very cool, very recent development. One of our scientists here, Lauren Edgar, she has been selected to be an astronaut candidate, and she very well could go to the moon or maybe even Mars in the next coming years to come. So pay attention to that. We'll be excited to watch her journey here from the Flagstaff campus. So I'm going to go into a little bit of a background of Geology 101 type topics before we get into the fun and fascinating details of the 1815 eruption, just so we can kind of get an understanding of how the Earth works. Well, the main thing that we need to first understand is how do we have these volcanoes, and Morgan may go into more details after, so I'm going to do a brief overview, is we can start with the source of heat in the Earth, that we live on an active planet where we have this heat from the core that is resonating up through the mantle and then coming up to the crust of the Earth. And this gives us our lithosphere. When that heated material that makes up the mantle floats to the surface and then it solidifies or cools, it becomes the crust of the Earth that we live on. And that has allowed for the outgassing from volcanoes that has released water, which can give us our hydrosphere, which can then has lead to the development of the biosphere, which can lead to the atmosphere, and how all of these different parts of the Earth interplay as a system, which leads to how everything on Earth can be affected by a major volcanic eruption. To take a look at how the Earth works, we can think of the Earth as like an egg. As geologists, we love to talk with our hands, just like Italians. So we also love to use metaphors. Geology loves to go into metaphor land, and food is always a great one. You can think of the Earth as an egg, where we have the egg yolk as the core of the Earth, which is generating that heat. It's moving up through the egg white, which is the mantle. And then you get to the crust of the Earth, where the action that we see happens, where we have the outer shell of the Earth. And this can lead us to understand how we have different types of rocks on Earth. And I do have some of the rock types up here listed on Earth on this diagram. There's three main types of rock, and some of you may know them. I've asked this question before, and I like when I get answers such as things like we have classic rock, we have hard rock, we have alternative rock, punk rock, country, all the different varieties of rock, and they're great answers. But here in geology, we're talking about the three main types of igneous, sedimentary, and metamorphic. A lot of the geological features you'll see around Flagstaff, which you'll learn in Morgan's next talk, I'm sure, are volcanic in origin. And you hear that word igneous. You can think of the root of that word, ignite. Where we've heard that word before, we can think of sources of fire, sources of heat. Well, geologists love our jargon, as a lot of scientists like to classify things and give fancy words to describe things. But here we can kind of break apart what these words mean. So we have that melting of the crust and plates converging, which generates friction, where we can have volcanoes. Then that rock comes up to the surface, and then what happens to rocks is a geologist's favorite ice cream flavor, rocky road. Rocks erode, and then we get beautiful sedimentary rocks, which leads to many of the national parks and monuments in the greater northern Arizona and southwestern region, such as the beautiful red rocks of Sedona and the Grand Canyon are sedimentary rocks. And then completing the rock cycle, where rocks get exposed to heat and pressure, they might get buried underground. That will lead to go on to form metamorphic rocks. And we think of the root of that word to morph or to change. We can think of a metamorphic rock in the context of taking a piece of clay, putting it in a kiln, and then it comes out as a solid ceramic. So these different aspects of how we can see those rocks change. In the Flagstaff area, we have a lot of great volcanic rocks, igneous rocks, and a lot of great sedimentary rocks. There are metamorphic rocks throughout Arizona, but you might have to go outside of this area, down towards Phoenix and Tucson, the Basin and Range area. A lot of the mountains are made of metamorphic rocks in that area. So our planet does not look the same everywhere. And why is that? Well, that's because of the Earth's tectonic plates, how the plates of the Earth move around. We are living on an active planet, and it has been divided into tectonic and oceanic plates. The tectonic plates are the continents that we live on above the surface, the lower density plates. Then the denser plates are the ones that underneath the ocean. And as these plates move around is really how we get the magic happening with geological processes here on Earth. The way these plates move is about the rate your fingernails grow. So if you trim your fingernails, you can think that's about how far the plate has moved that we're on since the last time you did that, to get a perspective. So they're moving millimeters per year, oftentimes. Some places might be faster if it's a more active region. But over geologic time, this can start to build up and start to change things. And if we get an understanding of where these tectonic plates are, we can kind of see the continents kind of fit together like pieces of a puzzle, where they used to be in a supercontinent and have drifted apart. And based on where they have drifted apart, we can start to notice some correlations, where we see some of the Earth's major volcano distribution sources. A lot of the volcanoes tend to be right around where we have these tectonic plates. And also, earthquake distribution also tends to follow these tectonic plates. There can be more exceptions with earthquakes, as they can happen in different places, but they tend to be very active along tectonic plates. And scientists, just like many scientists here at the USGS, can measure these plates and see the senses of motion that they are in fact moving, and we can see where areas of activity are and get an understanding of where volcanoes are likely to happen, where earthquakes are likely to happen, and so on. Also very interesting is how the major mountain belts of the Earth tend to involve right along these major plate boundaries, where if we see the Andes throughout South America, the Cascades in the Pacific Northwest, there are many places where tectonic plates are converging or colliding. And here we have what's known as a subduction zone. As geologists love to talk with their hands, if you have two plates colliding against each other, the heavier or denser one, the oceanic plate, will subduct or sink underneath the lower density continental plate that is essentially floating on the surface. And just like when it's cold out here in Flagstaff, if you want to warm your hands, you rub them together, you create some friction, you create some heat, and that will start to melt the crust. And depending on what that crust is made out of, what type of chemical components are in the mantle, you can start to develop volcanoes and start to develop different types of volcanoes. There can be a variety of volcanic features. Many you can see in the San Francisco volcanic field around Flagstaff. We have shield volcanoes, which are around in this area. And if anyone's been to the big island of Hawaii, some of the volcanoes there that are erupting lava form shield volcanoes. Then we have composite volcanoes, and we can think of these as the volcanoes that go boom. The things like Mount Vesuvius, the things like Mount Hood in Oregon, Mount Fuji in Japan, volcanoes that can lead to eruptions. And then we have cinder cones, which are smaller eruptions, which a great example of a cinder cone would be SP Crater to the north of us, or Sunset Crater National Monument, just a little to the east of here in Flagstaff. So these two major types of volcanic eruptions, we can have the non-explosive types, the effusive, or the ones that flow lava, like a slow-moving river, that we can see, the types that you might see in Hawaii, that leave behind volcanic rock known as basalt. And then you can have the more explosive volcanic eruptions, the volcanoes that go boom. And a great example of the explosive type of volcanic eruptions is the 1980 eruption of Mount St. Helens. And a lot of what controls the factors of volcanoes is the viscosity, or the resistance to flow, how the material moves when it's melted. And a way you can think of that is just how sticky the material is. If you have honey that's cold, it's not going to flow very far. If you heat that honey up, it's going to flow. So next time you have your pancakes or French toast, you can think about those properties of viscosity and how that relates to magma underground and lava on the surface. So how we form these different processes can lead to these different types of volcanoes. And here's a great example of showing the explosive style of eruption to get a sense of how this works, where we can have heat and pressure building up underneath the earth at that tectonic boundary, or not far from it. It can be inland from the boundary, but it's building that pressure. And just like when you heat up water in a tea kettle on a stove, that pressure will start to build up and eventually break through the lid and let you know your hot water is ready. Well, in the earth, the rock can hold some amount of that pressure for a while. It can melt, form lava flows, start to build up layers in a volcano. But eventually there can be a point where that pressure that builds up in the volcano is just too style of volcanic eruption, and how that can lead to effects of leading to catastrophic effects that can affect the whole planet and leave a lasting legacy to this day. So I hope we all took notes there for our basic, you just got your Geology 101 class. all together in 15 minutes, as I'm going to try to get through this talk in less than 45 minutes so we can have room to learn about the volcanoes of Arizona next. But if we were to just next take a look at natural disasters, as that is a big component of geology research, as the USGS has many volcano observatories to observe natural disasters and natural hazards. Where do we think volcanoes might fit on that list of major natural disasters? Well, if we take a look at the top 10 deadliest natural disasters by loss of life, we have several events on here that include floods, earthquakes, cyclones, tsunamis, where many of the disasters happen in places where there's large population centers. But here, volcanoes don't even make the top 10 list. As deadly as volcanoes are, and they can be, it doesn't mean that there's always large population centers around volcanoes. Even though they might be one of the more exciting aspects of geology to study, I think when we're all taking Geology 101, we dream about being volcanologists, hiking the world's volcanoes, studying them. At least I know I did. But we can see that as the list goes of the top 10 natural disasters, volcanoes do not even make the list, at least not at the direct loss of life caused by them. So then if we take a look at the top 10 volcanic eruptions in recorded history, we can see that Mount Tambora is at the top of that list with the amount of loss of life numbers that came from that eruption compared to other ones. So we've all heard of Krakatoa. Krakatoa seems to be a very commonly well-known volcano. And then that also occurred in Indonesia. Mount Vesuvius, for those who visited Italy, which a lot of the ruins from that volcano are preserved and left behind in the ash. Mount Pelée and some of these other ones were those who remember the Mount St. Helens eruption of 1980. That doesn't even make the list as one of the top 10 deadliest volcanic eruptions. So let's take a look next at where Mount Tambora is. Well, it's considered an active stratovolcano or composite volcano that's in Sumbawa, Indonesia. Has anyone ever been to this area? I never have. But I think it would be a very cool place to go and visit and see the volcanoes in this very active region of Indonesia. So the next question is, what is the difference between Mount Tambora and Mount Krakatoa? As it seems most people, maybe outside of this room, have heard of Krakatoa, but have not heard of Mount Tambora. Well, Mount Tambora occurred in 1815 and was much larger and much more destructive, which caused a global famine and ejected a lot more material into the sky, into the atmosphere, caused a lot more devastation. The 1883 eruption of Krakatoa was smaller. We have this VEI rating system of volcanoes, similar to the Richter scale for earthquakes. It was a magnitude lower on that scale and ejected much less geologic material into the atmosphere, into the surrounding areas. But the reason Krakatoa is more well known because of the invention of the telegraph, which led to the word to spread about the eruption of Krakatoa could spread much more rapidly, and people knew what was going on. At the time when Mount Tambora erupted in 1815, the word did not spread. By the time it may have been published in newspapers, it might have just been a little blip of a news story, and people might have said, oh, well, that's too bad for Indonesia, but how is it going to affect people in North America or in Europe or in other parts of the world away from Indonesia? But so that is the main reason is how the word could spread, and as far as the understanding of how devastating Mount Tambora would be, those effects of that were not known until later. But the one thing that they do share in common is they both are in Indonesia. And the Krakatoa is a small little isolated island, which is more or less in the eastern side of Indonesia. And then we have, or Krakatoa is more in the eastern side of Indonesia. And then the Mount Tambora is more on the western side of Indonesia. Both a very, very actively geologic place. So if we take a look at this, we can see here, this volcano was estimated to form about 57,000 years ago. And for a long time, no one knew that it was an active volcano. the active volcanoes were not very well understood at this time. There was local villages that lived around this area and throughout Indonesia, but people just knew this as a very big mountain that was here, that was somewhat of a landmark. No one really expected that it was going to erupt. No one had any idea that it was going to erupt in this area. And as this was a place at the time was ruled by the Dutch East Indies, and the British and the Dutch were battling for these territories at this time, with them being in this area at the time, they just used this as basically a landmark when they were navigating the Indonesian archipelago. This is what it looks like today. It was believed to be as high as 4,300 meters. So if you multiply that by about 3, that would be about 12,300 or 12,900 feet high. So very high in this area, especially as you're coming from sea level locations, a very high landmark in this area. Never been there yet, but this is what it might look like if you go there today. And you can see that crater in the interior is what was left of that explosion. That at one point in time, more or less, this volcano would have come up to a point and look like we might see what Mount Fuji might look like in Japan. So if we take a look at this area, some of us may have heard of the Pacific Ring of Fire, where there is many volcanoes and earthquakes throughout the Pacific Ring of Fire, where plate tectonics are happening, where plates are converging that go through Indonesia, up to Japan, up through Kamchatka in Russia, and then over to Alaska, where these plates converge. This shows a map here of the major volcanoes of Indonesia. And as we can see that there is several volcanoes along this Indonesian archipelago, with Tambora more or less towards the west, towards the eastern side, and Krakatoa more or left on the western side. If I have my directions correct, I should, I'm a geographer. And with Krakatoa was also closer to the larger population center of Jakarta. If we take a look next, as we're approaching the we're past the 210th year anniversary. This happened in 1815. So 2025, 210 years ago, we're still talking about this. We have this system known as the Volcanic Explosivity Index, similar to the Richter scale to measure volcanoes, which has a scale. And number 7 is the highest on there, where we can see that it's in the same bracket as the Yellowstone supervolcano eruption, and it's based on how much ejecta, or how much material, how much rock, ash, lava is erupted and ejected from these volcanoes and spread out to the surrounding areas and up into the atmosphere. And Mount Tambora is up there, is much larger. You can see where Mount St. Helens is on there in the VEI category of about 4. Mount Tambora erupted about 100 times more ash than Mount St. Helens did. And an estimate is that it would cover the whole landmass of Great Britain to about knee-high height with volcanic ash, to put into perspective of how much volcanic ash was erupted by this volcano. It erupted about 160 cubic kilometers of material, or about 24 cubic miles of material. And that's all of the rock and ash that went up into the atmosphere in the surrounding area. The explosion was heard on Sumatra more than 1,200 miles or 2,000 kilometers away. There's stories of sailors in the area that the captains told the sailors to man their guns. They thought they were under attack. They thought there was cannons going off. And the estimated loss of life toll was about 71,000 just directly. However, it is difficult to estimate the long aftermath effects, where historians have put together, with all the effects of the famine and the changes to climate and mass migration and turmoil that was caused by this, that the actual number of the indirect causes from the Mount Tambora eruption could be somewhere up in the range of more of the millions, up to World War I levels, if you were to factor all that was a result of it, which led to many diseases that were spread and things like that we'll touch on a little bit later. But why was this eruption so devastating and so explosive? Well, it's because it was so powerful that it sent ash so high up into the atmosphere. It went above the troposphere. We can think the troposphere is where we live, where Mount Everest is, where we have weather, where we have clouds, where planes fly. Well, the next layer up, we can think of where we send weather balloons, is the stratosphere. And when the ash gets up into there, those fine-grained particles, they stay up there. They don't just fall back down in rain. They don't get washed away. They don't get blown around and dispersed very well. They stay up there. And that's what really affected the temperature of the Earth. And it caused some rather odd behaviors to the planet, where as those small particles were reflecting light, that caused areas in the tropical and latitudes where most people tend to live, in between the 30-degree latitude zones and up into the 60-degree latitude zones, it caused cooling because the ash particles actually reflected the sunlight. But in the polar regions, it actually caused things to warm up slightly, as the ash particles, when there wasn't sun, it kept heat in because it transferred heat from the other areas in the stratosphere that normally didn't have ash into it up to the areas from the more polar latitudes. So it's interesting when we're looking at things like climate, how complex it interacts with the upper atmosphere. So we have these coarser ash particles that fell about 1 to 2 weeks after the eruption, with finer ash particles that stayed up in the upper atmosphere and the stratosphere for up to a year later, and then winds spread these all throughout the globe. And how this works is when the sun hits these particles, a lot of the particles reflect the sun and bounce it back so that heat does not hit the surface of the Earth, and therefore it causes a cooling event. And this didn't happen instantly. It took time for this to happen. Hence, it is known as 1816, the year without a summer, when the eruption occurred in 1815. So a lot of this caused a lot of mass confusion. And it wasn't until modern times, when ice core samples could be studied in Antarctica and Greenland based on the sulfate concentrations, where it would start to piece together how catastrophic this eruption was, where the events of this volcanic eruption could be traced back to the Mount Tambora eruption all the way in Indonesia. And we can see that there's some major spikes of this sulfate concentration, with big ones occurring right around just after 1815, with calmer periods before that and some calmer periods after that. Some of the aftermath of this was causing about the loss of 10,000 lives that occurred directly after. Many more that have been victims that remain unknown, but estimates up to 90,000 deaths that were caused from this volcano. And there's fascinating stories of sailors finding pumice rafts that were out in the ocean that they did not know how they got there. Pumice is a volcanic ash material that some might know from their spas and salons to scrub their feet with, but it's actually a geologic material, a volcanic ash that is so lightweight, so low density, it can actually float in the ocean. So this was found for many areas surrounded throughout the area, with thick clouds of volcanic ash that covered the area for weeks after, and just caused lots of destruction throughout the region for many years and months afterwards. And here's a record from one of the captains of a ship who was traveling in the area. He talks about the extreme misery to which the inhabitants have witnessed is shocking to behold. And he talks about the villages there were deserted. It was a very tough, difficult situation for the people in the surrounding areas as they were trying to find food. This left behind this year that had many names: the year without a summer, the poverty year, the year there was no number, and 1800 and froze to death. Overall, it only caused the temperature of the Earth to go down on average about, we can say about 1 degree Fahrenheit, or less than that in Celsius, maybe somewhere around 0.5 degrees. But that's taking a global average. And this shows how sensitive the Earth can be to subtle shifts in climate. Of just 1 degree temperature can really cause major food shortages all over the northern hemisphere, and just all the devastation that it caused. This also happened, as we saw on that map before, there was a few little spikes in sulfate concentration from that ice core. There was other events that led to this. It wasn't just the single eruption itself, but this also coincided, as many natural events happen, with other natural events that led to a more catastrophic catastrophic natural disaster. There was other volcanic eruptions that happened around the same time. In 1812 in the Caribbean, another big one in 1812 in Indonesia, another in 1813 in Japan, and another in 1814 in the Philippines. These were all in that volcanic explosivity index of 4, which is about Mount St. Helens. So there already was a substantial amount of ash in the atmosphere from this time, and it also coincided with something known as a Dalton minimum, a period with unusually low solar activity, as the sun can have cycles where it goes through increased activity and lower activity. So based on these weather patterns, really affected Europe and North America. And these are also places that we tend to have records that we know of to report what really happened in these areas. There's incredible stories of these unusual climatic effects that happen throughout the United States, in Canada, and Western Europe, with the coldest temperatures recorded anywhere between 1766 and 2000. 1816 was the coldest year in the Northern Hemisphere since 1400. The 1810s were the coldest decade on record, as well as cooler summers in parts of Europe. There's all kinds of stories where there was, in Philadelphia, there was frozen lakes. There was canals that froze in Amsterdam. People were skating on the Thames River in London. There's stories all over where there was massive crop failures. Some great records of this were kept by Thomas Jefferson, who was growing crops in Virginia at the time. Many different stories of how this affected this were in July and August. There was a river ice that was observed as far north as Pennsylvania, and the price of food caused the price of food to jump dramatically as we had eggflation early in the year, where we saw the price of eggs went up and everyone freaked out about that. Well, just to put some staple foods, for example, oats, they rose from 12 cents a bushel in 1815 to $1.50 or 92 cents a bushel in 1816, jumping from about $1.50 in today's prices to about $12.60 in today's prices. So also dealing with these crop failures and causing increase in prices and shortages, there was also less transportation and distribution networks to get food from the sources where they were to get them to people who needed them. And there's many stories of riots that formed in Europe where people were being concentrated, moving from rural areas, moving to more developed areas. Many stories of crop failures. I'm going to move through some of these in the interest of time so we can get through to the next topics. But many stories about how all these areas were affected. Also major effects in Asia as well, is causing people to move from more rural areas to cities. In China, there's stories of people that were growing rice. Their rice harvests were failing, which led to some people to change to growing opium as they wanted to grow a crop that would work, and just changed a lot of things. In India, there was delayed summer monsoons causing torrential rains, which led to the spread of diseases like cholera and things like that, and affected many of these areas. And now to some of the more interesting effects of how this volcanic eruption left a lasting legacy. Some of these effects are on art. Well, in Europe, they might not be known for the gorgeous sunsets that we get in the desert Southwest, but this ash in the atmosphere led to some unusual, spectacular sunsets in the area that has been left behind in the art from this era. And it's believed that this ash from Mount Tambora stayed in the atmosphere to cause this. And here's an example of a canal painting in England that shows this beautiful, looks like almost like an Arizona sunset that wasn't even painted until 1828, which is believed to be from some of that ash that is still flowing around. And this shows a painting here, two different examples, a painting that took place by the same painter in the same area, a painting from 1808 between 1810, and another painting that took place in 1817, where we can see a major change in the sky. And this leads to a question of why we have these beautiful sunsets like we have in Arizona. And that's because these particles in the sky in Arizona, we have a lot of dust in our atmosphere, especially when you go down south towards Phoenix. And as the sun is setting, is lower in the atmosphere, it reflects those particles of dust, and it reflects the oranges and reds and things like that, where the other colors, the blues and the greens in the spectrum of light, get absorbed or they're not reflected. And it leads to why we have these beautiful sunsets. And here's another example of this painting that was actually from Norway, an area that might not be known for many vibrant sunsets. And this is actually from 1893, a more famous painting known as the Scream. And this is believed to have come from the Krakatoa eruption of the later 1800s. So some other lasting cultural effects is believed to be the invention of the bicycle. As there was a lack of oats to feed horses, horses were starving, and people could not have horses to be able to transport food, which was the main transport at the time. So a German inventor named Karl Dreis led to inventing, he was a tinkerer, and he invented what he called the Dreisine, or the velocipede, which was known as the horseless transportation, the horseless method of travel, which led to the ancestor of the modern day bicycle. So because of this volcanic eruption, led a way to get around before the combustion engine was around or really took off. So we can thank the invention of the bicycle from this 1815 volcanic eruption in Indonesia. Another major effect that changed migration patterns in the United States was the westward expansion. As at the time, most of what was the United States at the time, people were living in the eastern colonies, places like Vermont, New Hampshire, New England. There was a lot of agriculture in that area. Well, this, due to a lot of crop failures in this area from these unusually cold temperatures, it caused people to start to migrate to what they saw as the fertile valleys of the Ohio River Valley and start to move to what we call now the Midwest, the areas of Ohio, Michigan, Kentucky, and moving further west in a westward expansion, which really started this trend of moving west to change the demographics of the country. And at this time, as often happens when there is natural disasters, it causes a revival in religious fanaticism, where people might get more interested in going to church, or they can't explain what's going on. No one knew what was going on. So there's many stories of Presbyterians moving out to the Midwest, and Presbyterians were known for being abolitionists. So a lot of the ending of slavery was believed, the ideas really started to proliferate for some of this westward expansion. There was also some other people, one notable at this time, a man by the name of Joseph Smith, whose family was farmers, who moved from Vermont to New York, moving further south to get away from this area, as in Vermont, they experienced a population decline of 10,000 to 15,000 people between 1816 to 1817, where many people were moving out of Vermont and out of New England, moving away, moving west, and with them caused change in demographics. Other effects are the effects on food science. Well, Justus von Liebig, who is a chemist in Germany, he grew up as a child in this area, in this period of famine. And he saw people starving, people not having food. And he is known as the father of the fertilizer industry, where he first started working with nitrogen and understanding how you could use nitrogen and extracting that using chemistry to help grow food. Some other inventions that were also accredited with his work at this time in food science was the invention of yeast extracts, which anyone who's been to Australia would know as Vegemite or Marmite in New Zealand. Also led to cubed bouillon for soups, and which led to the development of baby formula, which is all as a result of applying the science of chemistry from going through the hardships of the famine. And then another very interesting one with a lasting cultural effects is why I had Frankenstein on the intro slide of this presentation. And that is because as 1816 was a very cold year, it was affecting people all over. Well, some people who still had access to go to their cabins, this Mary Shelley was a part of that with John William Polidori and their friends. They would usually go from England and go through France and up to the Switzerland to go to their cabins. And they had a summer cabin. They enjoyed the summer recreation, which normally would be a beautiful summertime in Switzerland, in the Swiss Alps. But it was so cold, it was so rainy, they couldn't go outside. The storms brought lightning. And the story goes that they were just so bored in their cabin that Lord Byron, who was a part of their group, said, let's come up with an idea to keep ourselves entertained. Let's try to come up with the scariest story we can think of and write ghost stories to keep ourselves entertained. Well, Mary Shelley saw lightning at night with one of these storms, with these excessive rains and storms that caused from these climatic abnormalities. And she had the idea of bringing someone back to life, which she came up with the idea of Frankenstein, or the modern Prometheus, which was a direct result from this time frame. This also led, in the same group, also led to writing the story which later went on to become Dracula. There may have been stories that involved vampire-like figures throughout other cultures throughout history, but this is the first well-known one to be published that involves some romantic story of a vampire and the formation of Dracula. So if it wasn't for 1816, we would not have the Twilight series and all of the modern romantic vampire types of dramas. And as we are about to conclude, this reminds me of a great quote by the philosopher William Durant. Civilization exists by geological consent, subject to change without notice. And with this, I would like to say thank you to all of you who attended, and thank you to the Festival of Science. I think I may have 1 minute to answer a couple questions.